the handout I've given to you. This is so on Tuesday we talk about shearing force and bending moment. So for trusses that we have two force bodies, we have straight two force bodies, and so we have only TAB for one member, and we have if we cut it here or we cut it here, that we have only TAB or TAD. Now, but for free force bodies like this one, if we cut at D, make a cut at D. If we cut at D, that's F is not enough to achieve equilibrium, because F, if we say this is X prime and this is Y prime, summation Fy prime does not equal to 0. And so we need to add one force called shearing force to achieve equilibrium, and we also need to add M, bending moment. Okay. Now, for this is the same for two force bodies which are not straight. This is a non-straight two force body, which is AB here. Of course, for two force body, the forces on a two force body is the lines of action of forces on A and B acts on the line AB. The line of action is this one. The line of action of two force body AB is on the line AB. But if we make a cut at C here, if we make a cut at C, we find that it is not enough to just put F here. Okay, it is not enough to put only F here, because for this force A, we can use the same method, and we say this is A. We can put it in two forces, and this is A parallel, and this is A perpendicular. So for this part that F is not enough, and we need to have V and M to represent this to achieve equilibrium. It's okay. So we need V and M to achieve equilibrium. And talking about this, and M is called bending moment. M is called bending moment. So let's think about, for example, if AB were not a rigid body, what happens? If it is not a rigid body, and we apply force A and B here, we apply force P here, what what happens? It will deform. And how will it deform? And originally it looks like this, and it will look like this, right? Oh, sorry, it will look like this. Oh, sorry, something like this. So this is bending. So we have something called bending moment. So this bending moment is related to M. Okay. So if AB were not a rigid body, that it will become something like this. So we have bending. So we have bending moment. Is that okay? After you have drawn this, then let's go to the next page. If you finished drawing this, then let's go to the next page and sample problem 7.1. Determine the internal forces in member BCD at point K. So point K is here. Point K is here, and the distance is 1.5 meter. And the frame was previously analyzed in sample problem 6.5, which is on page what of the notes? Page this one, page 50. Page 50 of the notes. Page 50. Page 50. Now, how should if I ask you for determine the internal forces at some point, like point K? Now, because we have analyzed this frame, so we take a single member. We take a single member A. We take a single member BCD. And let me repeat the results for you. And this is this one. B is 1,200 Newton, and This one is it looks like something like this. And this is B, C, and D. And point K is here. The distances are what? 3.6. 3.6 meter, and this is 1.5. And this is, I think it is 2.4 meters. So, okay, it looks like something like this. We take a single member, we only take one member. Because K is on BCD, so we take BCD. After that, this is the first step. A is this one, and B is make a cut BCD at point K. Cut BCD at point K, and you can write both. You can draw both sides, but you can draw only one side. It is so. It is also fine. I will draw both sides. B is here. K is here. C is here, and D is here. Maybe I draw it. I make it a bit to the left. I cut B because we want to determine the forces at point K. So we cut BCD at point K. Okay. For the forces, we already know. We put the forces. We can put the forces first. And of course, this one is 1.5 meter. You can draw both sides, and you can draw only this side, only the left hand side or the right hand side. The result will be the same. So we make a cut here, and we make a cut here, and the left go to here, then the right go to here. Now, then what next? The next thing is, what do we need to draw here? For two force members, it is easy that we have F here, right? We have F here, and then this is the and then action and reaction. It is okay whether to write draw outward or inward. That's both ways is okay. But for free force bodies or multiple force bodies, what do we need to do? We also need shearing force and bending moment. Okay, if it is going up to the left, and then so if it is going up on the left, what do we need on the right? If this goes up on the right, we should go down. And of course, if we have and we need moment as well. Moment is if we go counterclockwise on the left and on the right, then we will have clockwise. Okay, we need all these three things. You need to count 1, 2, and 3. B, F, and F. So it's okay for both because it is not a two force body. So if you make a cut, you need all three things here: actual force and shearing force and bending moment. After that it is the most difficult part is here, and the rest is okay. So let's take a look of this part. So we take a look at B and K, BK. Now for the part BK, we put in summation fx equal to 0. Summation fx equal to 0, and summation fy equal to 0, and summation moment equal to 0. And we can take point. It is okay to take point B or point K. Let's take point K. Now we have for summation fx equal to 0, we have, what do we have? We have f is equal to 0, right? Because we have only one force on the x direction, on the x-axis. Now, and for Fy, I will give you time to write down. For Fy, which is then we have V minus 1.2 kilonewton equal to 0. So V is equal to 1.2 kilonewton going up. And for mk equal to 0, we have m plus 12, how much? 1.5 meter times 1200 Newton. Sorry, I should put it to the left. Equal to 0, so m is equal to what? 1,800 Newton meter clockwise. Okay, and these three are the results. Remember, the result has three parts now: F, V, and M.